This video is going to be so fetch. Let's talk about the mean value theorem. So first, a preliminary result known as Rolle's theorem. We got f of x, it's a function, it's continuous on the interval a, which includes its endpoints. This is a connected compact set. It's differentiable on the interior. We're not going to address derivatives at the endpoints, but at least except at the endpoints it has a derivative. And our final assumption is that f of a equals f of b. The value of the function at the endpoints is equal. Then the conclusion of the theorem is that there's some point in between a and b where the derivative is 0. Now here's a picture to sort of show what we're given and what we're concluding. So here is our interval from a to b. The function just has to be continuous from left to right and have a derivative on the interior. Also, the height at the left endpoint is equal to the height at the right endpoint. So if I label this as f of b and I label this as f of a, those are at the same height. Now I'm going to connect them with a nice continuous differentiable curve, maybe something like this. So the conclusion of the theorem is that there's at least one point, possibly two or more, but at least one point, and I'll label it as C, where the derivative is 0. Now with this picture, what I did is I picked the maximum value. Okay, now what we know from earlier results is that wherever the maximum value occurs, either the derivative doesn't exist or the derivative is 0. And our conclusion that we're going for is that there's somewhere where the derivative is 0, and you kind of see a lot of how this proof is going to go. So the function is continuous on a compact interval, and therefore it has a max and a min. If either the max or min occurs at an interior point, then because the function has a derivative there, the derivative must be 0. Okay, that's what this picture sort of illustrated, and that's most of the work. Okay, wherever the max and min are, if either one of them is inside the interval, either the derivative is 0 or doesn't exist, but we assumed the derivative existed everywhere inside the interval. Therefore, if a max or min happens inside the interval, the derivative there must be 0, and we're done. And one way of looking at this is that, yeah, if the function is going up towards its maximum and then decreasing away from it, that's where you get your maximum, and you can see a derivative being 0 there. Yeah, or at mins, yeah. Now, suppose you don't get so lucky. Okay, the max and the min don't happen on the inside. If they don't happen inside the interval, they have to happen at the endpoints. But the value at the endpoints is equal. So if the max and the min both happen at endpoints, and the value at the endpoints is the same, well then the max value is the same as the min value. The only way a function can have a maximum and minimum be the same value is if it's constant, and we already know that constant functions have 0 derivative everywhere, in which case pick any point inside you want. And we're done. Wherever the max and min happens, if it's inside the interval, there your derivative is 0. If both happen at endpoints, then your function was constant and the derivative was 0 everywhere. And that's Rolle's theorem. Now we can state the mean value theorem. Okay, suppose f is continuous from a to b, including the endpoints, and differentiable on the open interval. This is the same set of givens so far, but we're dropping the requirement that the value be the same at the endpoints. Our conclusion is now there is some point inside where the derivative isn't necessarily 0, but it's this quotient f of b minus f of a over b minus a. The proof is pretty straightforward. Okay, whatever that quantity is on the right, I'm calling it m. I want somewhere the derivative to be equal to this m. I define a new function. G of x is just m times x minus a. But m is just some real number. A is just a real number, and therefore g is a linear function. It's a linear function, and therefore it's continuous on the interval from a to b and differentiable on the open interval. And notice that its derivative is exactly m everywhere. Okay, I made a linear function with slope m. Now g of a is 0, just plug it in, and g of b is exactly the same as f of b minus f of a. If you replace m is equal to f of b minus f of a over b minus a, and then multiply it by b minus a, you'll recover exactly f of b minus f of a. So f of a minus g of a, okay, remember g of a is 0. Great. But that's just as a matter of computation the same as f of b minus the quantity f of b minus f of a, which is f of b minus g of b. So f of a minus g of a is equal to f of b minus g of b. So now I have a function that takes the same value at the endpoints, but since f and g were both continuous from a to b and both differentiable on the open interval, then f minus g is continuous on the interval and differentiable on the open interval. And now I've got a function, this function being f minus g, that I can apply Rolle's theorem to. So I will find some point on the inside, and I'll call it c, where the derivative of f minus g is equal to 0. But the derivative of f minus g is just f prime minus g prime, and g prime is exactly the constant m. And now if I just add m to both sides, we get some point on the inside where the derivative of f is m, which was our goal. So we really did just apply Rolle's theorem to a different function f minus g. And tilted is a reasonable way to think of it because the function f minus g is the function f of x minus a line. And if you subtract a line from a function, it kind of looks like it's just tilting over. Yeah, a function minus a line. I mean, if we want to be really technical, it's not actually a rotation. It's not a tilting, but it's close enough. So here's what this looks like. Okay, we've got our function that is continuous and has a derivative, but now it doesn't necessarily take the same value at the endpoints. This is our function f of x. We make the function g of x, and it's just a line of the same average slope. Okay, so the average slope of f of x on this interval would be exactly the difference in the y-coordinates over the difference in the x-coordinates, and I just made a line of the same slope. Now if I take the difference, we're going to end up with something that looks kind of like this, but it's been sort of not tilted, but squished in a certain way that now its height is equal at both endpoints, and I can apply Rolle's theorem. Moving on to a new result, if f is differentiable on an interval, and the derivative is not negative, then the function is increasing on this interval. And we have already proved the converse of this. Remember, we've shown if a function has a derivative and is increasing, then the derivative is not negative. Now we're going the other way. If the function has a derivative and the derivative is not negative, then it's increasing. So assume to the contrary, okay, that it's not increasing. For the function to not be increasing, there are 2 points where the left endpoint is sent to a larger value than the right one. So a is less than b, but f of a is bigger than f of b. This doesn't have to be true for every pair of points in order to violate that the function is increasing, just for one particular pair of points. Remember, the definition of increasing would be for every pair of points, such and such. So to violate that, you just need one pair of points that violates the increasing property. So a and b are quite specific. Okay, they're not general or arbitrary. There is one pair of points, a and b, with this property. Well, what happens then? So all we know is that we have a function where a is less than b, and f of a is bigger than f of b. But this does come right after the mean value theorem, so what do you think we could do with f of a being bigger than f of b? I wonder, what can you tell me about the slope of this line? So f is differentiable on the interval. It's therefore differentiable from a to b, because a and b are both in the interval, and therefore every point in between is in the interval. So it's continuous from a to b and differentiable on the interior of a to b. By the mean value theorem, there must therefore be some point in between a and b where the derivative is f of b minus f of a over b minus a. But b was larger than a, so the denominator is positive, but f of b was smaller than f of a, so the numerator is negative. So overall, we found a place where the derivative is negative, which contradicts our given that it never is. Moving on to another definition that you would have encountered back in Calc 1, but we're going to define it slightly differently. Okay? Suppose f is defined on an interval a, and you have the following property. If you take 2 points in the domain, okay, and you connect the corresponding points on the graph, so you x1 and x2 are both in the domain, and you connect x1, f of x1 and x2, f of x2 with a line, call that L of x. If the graph of the function is consistently above the line connecting those 2 points, so the graph of the function is above the line, we call that concave down. here's what this would look like. Okay, I'm going to draw a picture matching what we all expect concave down to look like, something like that. But here's what we have. Any 2 points I pick in here, let's call them x1 and x2. So this is now at height f of x1. This is at height f of x2. If I connect these with a line and only look at in between these 2 points, notice that the graph is above the line. And this doesn't really matter where I draw the line. If I connect any 2 points on the curve, the graph is consistently above the line I'm drawing. That's a geometric definition of concave down. Notice that this definition has nothing to do with derivatives. Okay, if the reverse holds, if the graph is always below the lines that you draw, then it's called concave up on that interval. Okay, concavity in terms of tangent lines, what do you mean? Concave up means tangent lines are below the graph, while concave down means tangent lines are above the graph. So this is sort of true. If I draw my typical concave down shape, if I draw tangent lines, then the tangent lines are above the graph, and that could be concave down. Whereas if I have concave up, tangent lines are always below the graph. So that's true enough as long as tangent line is a reasonable definition. But remember, I didn't want to talk about derivatives, and tangent lines aren't always connected to derivatives anyway, so I didn't want to bring that into it. The geometric definition given earlier is really quite general. So try to work on this problem, which matches up the geometric definition of concavity that we just introduced to what you would remember from Calc 1 involving second derivatives. And as always, go ahead and take a moment to comment or subscribe to the channel. It helps me keep track of who's paying attention and who's utilizing these videos. Okay, hopefully you also paused there and worked through this, and now you see that if the second derivative does exist, then the sign of the second derivative can help determine concavity. But concavity, as I've mentioned, is a definition that's purely geometric and doesn't actually rely on derivatives. So let's go ahead and bring more and more terminology into the mix. Suppose capital F is a function whose derivative is little f on a set A. Then on that set A, what we're going to do is we're going to say capital F is an antiderivative of f. It's a function whose derivative is little f. Are they? So we use this symbol, this scripty s thing, to mean the set of all antiderivatives of f. And right now I'm just going to call them antiderivatives. I'm not going to call them integrals because that's a different idea that we haven't even introduced yet. So this is just a set of antiderivatives. So let's work through a result. Okay, suppose f is continuous on the interval from a to b, including the endpoints, and the derivative is 0 everywhere on the interior. Then f of x must be a constant. Now we happen to know constants are antiderivatives of 0. Okay, the derivative of a constant is always 0. So we already knew that constants are antiderivatives of 0. This is saying they're the only antiderivatives of 0. If you have a function whose derivative is 0, then that function had to be constant. Right, so the set of antiderivatives of 0 are the constant functions. Suppose to the contrary that the function f that satisfies all these properties isn't constant. There are 2 points where the value of the function is different. Okay, so a prime and b prime are just 2 points where the value of the function is different, and I'm going to go ahead and assume that a prime is the left one and b prime is the right one. I'm not assuming that f of a prime is bigger or less than f of b prime, just that it's not equal, but I'm not assuming which way. So since I'm looking at a subinterval, remember the function is continuous all the way from a to b, so if I take 2 points on the interior and make a new interval, it's continuous there and has 0 derivative there. Now I can apply the mean value theorem. Well, b prime and a prime are different, so that denominator is not 0, but I assumed b prime and a prime were 2 points where the function was different, so the numerator is not 0. So I have a ratio of 2 non-zero numbers, so f prime of c must not be 0, which contradicts the fact that the derivative was 0 everywhere. So the mean value theorem comes to the rescue again. Okay, if a function always has derivative 0, it can never change its value. So here's the picture of the proof we just did. So we are going to assume that f prime is 0 all the way from a to b. But we've also assumed there are 2 points where the value of the function is different. So there is some a prime and some b prime where f of a prime is not the same as f of b prime. I've just gone ahead and said f of a prime is less than f of b prime, but it doesn't really matter. So since the function was continuous from a to b, it's also continuous from a prime to b prime, and since the derivative was 0 all the way from a to b, the derivative is also 0 from a prime to b prime. Now I apply the mean value theorem and find there must be a point somewhere in between where the derivative is equal to this average slope, which isn't 0, which contradicts our assumption that the derivative was 0. Okay, here's another sample problem to work on. And this is a really nice result to have in our tool belt. So if you've done this, then you've shown something really nice, okay? Because we were able to show that the antiderivatives of 0 are just the constants, any 2 functions that are antiderivatives of the same thing can only differ by a constant. That's what you've got here. And this plus c is the same from Calc 1 general integration problems. If you're looking for all possible antiderivatives, well, if 2 things are both antiderivatives of the same result, their difference can only be a constant. So really, up to a constant difference between them, they're all the same basic function. And that's the plus c. It says the antiderivatives of x squared, they all look like x cubed over 3, possibly with a constant term different between them. So the set of all of them is just x cubed over 3 plus some constant. Yeah, right. Yeah, so remember, we haven't done integration. We're only talking about anti-differentiation, and we don't know that these are the same thing yet. Okay, so let's talk some more about antiderivatives. Suppose f of x is an antiderivative of f. We know that any antiderivative must differ by a constant, but that constant is something we have to be pretty careful about. It only actually needs to be constant on connected sets. So for example, what are the antiderivatives of 1 over x? Both the natural logarithm of the absolute value of x, there's a function whose derivative is 1 over x everywhere except for 0. But also this function g of x. When x is positive, you have log x. But when x is negative, you have log of the absolute value of x plus 2. Notice that plus 2 doesn't affect derivatives. Okay? We added a different constant for negative numbers than for positive ones, but we didn't actually change where the function is continuous or where the derivative exists, because the function doesn't even exist at 0. So the constant that got added to log x was 0 for positives and 2 for negatives, and that was fine. Because the domain isn't connected, you can add a different constant on each piece. Yes, so this constant c is not just a fixed number, it's a function that is constant on connected pieces of the domain, technically speaking. For most of the functions we deal with, the domain is all reals, which just has one component. But sometimes you can have a function whose domain comes in several pieces, and this constant only has to be a constant on each piece. Now, we did prove the intermediate value property some time back. Okay? If a continuous function on a compact set takes 2 values, compact connected set, takes 2 values, then it takes all values in between. Okay? We also know that if a function has a derivative, then it must be continuous. Therefore, any function that has a derivative must satisfy the intermediate value property. But is it possible to have a derivative and that derivative not be continuous? So we kind of want derivatives to be as nice as the functions that generate them. I mean, if the function has a derivative, then the function is continuous. Does its derivative have to also be continuous? We want the answer to be yes. But yeah, because that would be so nice. Womp womp. Indeed, it's totally possible for a function to have a derivative, but that derivative is not continuous. So here's an example. Okay, we're just going to assume that the sine function behaves like we all expect it to. So define the function f of x as follows. For every value other than 0, you take x squared times the sine of 1 over x, and if you plug in 0, you get out 0. So now the function is defined everywhere. In fact, it's differentiable everywhere. So first, you can show it's continuous everywhere, but you can actually compute the derivative at 0. And what you'll find is that the derivative is not a continuous function. Be nice. You too. So there is some value in these degenerate-looking examples that really illustrate how these definitions are subtly different from one another. The counterexamples and examples generated by mathematicians over the years have really helped illuminate exactly what's going on. So here's what the function looks like. Okay, we are looking at x squared times the sine of 1 over x. What does this function look like? Well, the sine of 1 over x, it's trapped between 1 and minus 1 because the sine function is trapped between 1 and minus 1. But 1 over x, as x gets close to 0, escapes off to infinity. So you're plugging numbers into the sine function that are getting bigger and bigger, faster and faster, which means the sine function has to do its oscillations faster and faster and faster and faster. So this is basically what the curve sine of 1 over x looks like. As you squeeze in towards 0, the sine curve has to go up and down infinitely many times. But we're multiplying it by x squared. Okay, and now that changes things. While the sine curve is going up and down, up and down, up and down, I'm multiplying it by x squared. And what's happening to x squared as x approaches 0? X squared is approaching to 0. So by the squeeze law, okay, what you actually find, if this is the curve positive x squared, and this is the curve minus x squared, because sine goes back and forth between 1 and minus 1, our curve goes back and forth between these two things. So it goes up and down faster and faster, but trapped between these two things here. So here is our curve x squared times the sine of 1 over x. It is continuous at 0. And you can compute the derivative away from 0 just by using, exactly what derivative laws you'd think. And we plug the hole by just declaring that f is 0 there. That will make it continuous. And then you can compute the derivative manually at this point, but you'll see that the result is not a continuous function. So let's get to that. So away from 0, just by using traditional derivative laws, the derivative is just 2x times the sine of 1 over x minus the cosine of 1 over x. Okay. And this is fine. As long as x isn't 0, there it is. Therefore, the limit as x approaches 0 of f prime doesn't exist. Okay. Remember, the derivative was essentially x times the sine of 1 over x, which goes to 0 by the squeeze law. But then there was this other term of just cosine of 1 over x. And as the 1 over x escapes to infinity, cosine goes up and down between plus or minus 1 infinitely many times, and therefore doesn't have a limit. It's not settling down on a value as x approaches 0. So f prime doesn't have a limit at all as x approaches 0, because from both left and right sides, it's going up and down in between plus or minus 1 infinitely many times. So if f prime of 0 exists, f prime can't be continuous at 0. Okay, because this limit doesn't even exist, it doesn't equal f prime of 0. So all we have to do is show f prime of 0 exists, and we'll have found something that has a derivative, but the derivative is not a continuous function. So we just do this directly through the limit quotient. We're not trying to compute f prime in general, just specifically the derivative at 0. So we take the limit as x approaches 0 of this quotient. F of 0 was manually declared to be 0, and now I'm just going to cancel off one of the x's from f of x. Remember, f of x was x squared times the sine of 1 over x, so I cancel out one of those x's. And by the squeeze law, the limit as x approaches 0 of x times the sine of 1 over x is 0. So the derivative exists at 0 and is 0. But the limit as x approaches 0 of the derivative doesn't exist, and therefore the derivative is not continuous. Now let's introduce something known as Darboux's theorem. Okay. So we now have an example of a function that has a derivative whose derivative is not continuous. But Darboux's theorem says derivatives actually still satisfy the intermediate value property even if they're discontinuous. Which does sound a little odd. The intermediate value property says if you take two values, you take every value in between. So how can that happen without being continuous? Well, if we manage to show that derivatives satisfy the intermediate value property, then since we have an explicit example of a function that has a derivative that isn't continuous, we will know it's possible for discontinuous functions to satisfy the intermediate value property. So here's the statement of the theorem. If f has a derivative on an open interval, then f prime satisfies the intermediate value property on that interval. Specifically, if it takes two values, then it takes all values in between. First, what we'll do is we'll show if the derivative is positive at one point and negative at another, it must be zero somewhere in between. So suppose now that x and y are 2 points in A, and x is less than y, x is just the left one. Also, let's assume for the moment that f prime of x on the left is negative and f prime of y at the right is positive. We just need to find some point in between where the derivative is zero for this partial step. So here's what we've got. Okay. We have a function, it's continuous on an interval a, that's great. We have x is less than y. Also, f prime of x is negative and f prime of y is positive. So in terms of pictures, we're going to rely on tangent slope as a notion. So f prime of x being negative means I don't really know what height f of x is at, but it has this negative looking tangent slope. And I don't know what height f prime of y is at, could be up here, but it has this positive tangent slope. So since the function is decreasing, okay, then since here it's increasing, what we need to argue is that somewhere in between it turned around and had a point that was a local minimum, and therefore, since the derivative is assumed to exist, the derivative there must be zero. So x is less than y and f prime is negative, f prime of y is positive. Since f is differentiable on the interval, it's definitely continuous, therefore continuous from x to y. Why am I stating all this? Because I want to show it has a minimum value. Okay, remember our little geometric argument relied on something happening at the minimum value. We should probably prove that it's there. So since the function is differentiable, it's continuous, therefore it has a minimum. So the first thing to claim is that the minimum can't happen at the endpoints. Remember, if we're restricting the domain to just be from x to y, this minimum value might occur at an endpoint even though the derivative in the global sense is not zero there, because in the restricted domain, the derivative can't be presumed to even exist there. So we're going to claim and then show that the minimum value doesn't occur at an endpoint. So let's revisit that picture we had. Since f prime of x is negative, this can't be the minimum value because the values here have to be lower. And since f prime of y was positive, this value can't be the minimum because these values here are lower. That's what we're about to show, but the picture sort of gets that across. That with non-zero derivatives at the endpoints, in the following arrangement, neither one of them can be the minimum. So the technical proof is f prime of x, remember, was negative. So negative 1 times that is positive. I'm going to let that be epsilon. Since the limit of this difference quotient is f prime of x, eventually we are within epsilon of it. But to be within epsilon of f prime of x is to exactly be negative, in between negative 2 epsilon and 0. Okay, pause here if you need to and work through these inequalities. So why do I know that this first statement here is true? Because the limit of this is this. It gets as close as I want. It gets epsilon close. But f prime of x, with a minus in front of it, was just epsilon. How can I be epsilon far away from epsilon? I can be in between 0 and negative 2 epsilon. So since the fraction is negative and the denominator is positive, okay, the numerator must in fact be negative, meaning as z is bigger than x, f of z must be less than f of x, so x is not the minimum because f of z was actually smaller. And that exactly backs up what our picture showed. It is going to drag on for quite a bit longer, I'm afraid. Very similarly, at the right endpoint, okay, this is converging to f prime of y. If I just set epsilon to be equal to f prime of y, it must be epsilon close for any epsilon, specifically that one. Replace this with epsilon, and now how can this quantity be within distance epsilon of epsilon? It must be in between 0 and 2 epsilon, so it must be positive. Since the denominator is negative, that means the numerator must also be negative, meaning f of z must be smaller than f of y, so f of y was not the minimum. So now our function has a minimum because it's continuous, but the minimum doesn't occur at an endpoint, therefore the minimum must occur at an interior point, and since the derivative exists on the interior, the derivative there must be 0. So, assuming f prime of x was negative and f prime of y was positive, where x was the left and y was the right, some point in between the derivative is 0. This is a very partial way to getting an intermediate value property. If the derivative goes from negative to positive, then it was 0 somewhere in between. And it is going to go on for quite a bit longer. Yeah, be careful what you wish for. I mean, if you really like the intricacies of putting together step-by-step proofs, every once in a while you're going to get a pretty long and unpleasant one. Okay, but let's keep going. So what we know is if x is less than y and f prime goes from negative to positive, it must have been 0 somewhere in between. You can basically run the exact same proof, instead of looking for minimums, looking for maximums, to show that if a function has a derivative that goes from positive to negative, then somewhere in between the derivative was 0. Now what we need to do is suppose that a function goes from one value to another, and c is somewhere in between. What we're going to do is we're going to find some point where the derivative is c. So very similarly to how we proved the mean value theorem, I'm going to replace the function f of x with g of x, which is f of x minus c times x, where c is that value we were hoping to find the derivative equal to. Now f prime went from less than c to bigger than c. So what about the derivative of g? The derivative of g is exactly f prime minus c. Okay? And that's just from how we defined the function g. If all you do is take this as your function g and take its derivative, you're going to get f prime minus the constant c. So since f prime goes from less than c to bigger than c, g prime goes from less than 0 to bigger than 0, and by the work we've just done, somewhere in between the derivative of g is 0. But g prime can only be 0 if f prime minus c is 0, in other words, if f prime is c. So we found a point where the derivative of f was exactly the value c that we wanted. So again, similarly, okay, if it went from bigger than c to less than c, you pretty much run the same argument and you find somewhere in between the value must be equal to c, the value of the derivative must be equal to c. So we've proven Darboux's theorem, okay, we satisfy the intermediate value property. If the derivative takes two values, then somewhere in between it takes every value in between. But we do have an example of a function that has a derivative that isn't continuous, so it's definitely possible for a discontinuous function to have an antiderivative. It's also possible for a discontinuous function to satisfy the intermediate value property. Okay, since we found a function whose derivative is discontinuous, there's a discontinuous function that has an antiderivative. It is totally possible to antidifferentiate discontinuous functions, but not functions that fail to satisfy the intermediate value property. Darboux's theorem tells us derivatives satisfy the intermediate value property. So if you draw a picture of a function that doesn't satisfy the intermediate value property, it cannot be antidifferentiated on that interval. So that's actually going to close out our discussion of the mean value theorem. I hope you found it illuminating. Come on back for more content.